Hello everyone, welcome to this session on CET chemistry. In this session, we'll be discussing some of the questions from CET 2017 chemistry question paper. So let us look at these questions one by one and answer them accordingly. Okay, this is the first question. So if 3.01 times 10 power 20 molecules are removed from 98 mg of H2SO4, then the number of moles of H2SO4 left are. So basically, when you say 1 mole, one mole of H2SO4. So it is nothing but equivalent to your molecular weight. Molecular weight of H2SO4. And what will be the molecular weight of H2SO4? So it is nothing but 2 times 1 plus 1 times 32. That is for sulfur. And for oxygen is 4 times 16. So it will be 4. So total it is equivalent to 98. So it is equivalent to 98 grams. So if you take 1 mole of H2SO4, it is equivalent to 98 grams. So from that, we can say that 1 mole of H2SO4 equivalent to 6.023 times 10 power 23. So here we are discussing H2SO4, which is a molecule, so it will be 6 times 10 power 23, 6.023 times 10 power 23 molecules. So that is for 1 mole. So obviously, if you say 1 millimole of H2SO4, so this will be equivalent to 98 milligrams. So it is equivalent to 6.023 times 10 power 23. Because you told milli, it will be 10 power minus 3 molecules. So these will be the number of molecules. So which is equivalent to 6.023 times 10 power 20 molecules. So because in the question they told 98 mg of H2SO4. So first let us calculate how many molecules of H2SO4 are present in 98 mg. So which is nothing but equivalent to 6.023 times 10 power 20. So from that 3.01 times 10 power 20 molecules are removed. So that is equivalent to how many moles? That's the question. So so from this 6.023 times 10 power 23, let us remove minus 3.01 times 10 power 20 is equal to, so this is 10 power 20. So it will be 10 power 20. So is equal to, so let us take 10 power 20 common. So I'm taking this approximately equivalent to 6. 6.023, I can just take it as 6. So it will be 6 minus 3.011. So it's approximately equivalent to 6 minus 3 will be 3. 3 times 10 power 20. So 3 times 10 power 20 molecules are left. But here the answers are in moles. So we have to calculate in terms of moles. And we know that 1 mole is equal to 6.023 times 10 power 23. So 3 times 10 power 20 molecules will be equivalent to how many moles? So how many moles? So it will be 3 times 10 power 20 divided by, I'm taking approximately 6. 6 times 10 power 23. So it becomes equal to 1, 3 1s are 3, 3 2s are 6. So it will be 1 by 2, which is nothing but 0.5 times. So it will be 10 power 20 minus 10 power 20, 23 will be, it will be 10 power minus 3. So it will be 0.5 times 10 power minus 3 moles. So this will be the answer. So if you look at the options, B will be the correct answer. So that's how we solve this question. Let us look at the second question. So the correct set of quantum number for the unpaired electrons of chlorine atom is, so to find out the quantum numbers of that unpaired electron which is present in the chlorine atom, let us first write down the electronic configuration. So electronic configuration of chlorine atom will be electronic configuration of chlorine atom. So chlorine basically it is 17 atomic numbers. So electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p5. Now, when you say this 1s2, 2s2, 2p6, 3s2, all the orbitals are doubly occupied, so they are paired up. So there are no unpaired electrons. But when you look at 3p5, there is one unpaired electron which is present. So if you look at the structure, orbital diagram, it is actually this. So you put one here, one here. So only pairing takes place only after each orbital is filled with one electron each. So that's what Hund's rule say. So 4 and then 5. So they're asking you to find out the quantum number for unpaired electron. So here the unpaired electron is this. So we have to find out the quantum number for this electron. So now, so here the value is 3p5. So your n value will be 3. So this will be your n value, whichever is that highest n value. And you have what is called azimuthal quantum number, which is L. So L will be different for different orbitals. For s orbital, it is 0. So for p orbital, it is 1. So for d orbital, it is 2. So like that it goes on. So here it is p. So which is why it is 1. And you have magnetic quantum number. So magnetic quantum number values range from -L through 0 to +L. So you have 1 here. So it will be -1, 0, +1. And if you look at this orbital diagram, so you can say this is equivalent to your -1, 0, and +1. So from this you can say this unpaired electron is present in the +1. So your ml value will be +1. And if you look at spin quantum number, so that is ms. So you have one unpaired electron, so which can be taken as plus or minus half. So it can be, so that electron can be rotating clockwise or anti-clockwise. So which is why you can just take it as plus or minus half. So from this we can say that you have n value 3, L1, ML1, and MS plus or minus half. So from the options given, C will be the correct answer. So that's how we will solve this question. Let us look at the third question. The electron negativities of carbon, nitrogen, silicon, and phosphorus are in the order of. So we have to keep these elements in the whatever order fits in one of these options. So let us try to solve this question. So if you look at periodic table, you have first carbon, then nitrogen, then you have silicon, then phosphorus. So this is how in the periodic table these elements are arranged. So so carbon and nitrogen belong to second period, and silicon phosphorus belongs to third period. Now, as we know that if you go from left to right across a period, so what happens to the size? Size actually decreases. And what happens if you go from top to bottom in a group? So the size actually increases. So it is due to the addition of extra shells. So the size increases from top to bottom. Now, so if you say electronegativity, it is nothing but the tendency of an atom to attract the bonded pair of electrons towards itself. So let us say you have HCl. So these bonded electrons, so how much it is pulled? So we say chlorine is more electronegative. So these bonded electrons are pulled more towards chlorine. So your electron cloud will be something like this. So you can say the bonded electrons are spending more time on chlorine compared to hydrogen. So which is why you say delta negative and this delta positive. So chlorine is more electronegative. So the definition is like this: electronegativity is the tendency of an atom to attract this bonded pair of electrons towards itself. More the tendency to pull the electrons, more electronegativity. So that's how we say. So now when you look at the sizes and explain this electronegativity, let us say you have a size of an atom something like this in bonded state. So you have your nucleus, and the bonded electrons are somewhere here. So if the distance from the center of the nucleus to the electron which is bonded is less, So it can be pulled easily. So you can say highly electronegative. This will be highly electronegative. But if you have a bigger atom like this, the distance from the center of the nucleus to the bonded electrons will be more. So the bonded electrons cannot be pulled inside, pulled in the electrostatic field of that atom. So you see, you can say that this atom will be less electronegative compared to the one which is smaller. So you can say that atomic size is inversely proportional to electronegativity. So basically, if the size is more, electronegativity will be less. If the size is less, electronegativity will be more. So that's how we define it. Now, so obviously, if you go from top to bottom, the size increases. So electronegativity will be definitely less. So from that, you can actually say that silicon and phosphorus will have less electronegativity compared to carbon and nitrogen. Now, within these elements, you have to tell which of them has lower electronegativity. So obviously, if you say from left to right, the size actually decreases. If the size decreases, what happens to the electronegativity? Electronegativity will increase. So from that, you can say that silicon will be less electronegative compared to phosphorus, then compared to carbon, compared to nitrogen. So that's how we write down the electronic configuration, electronegativity order of the given elements. So from this, you can say option B will be the correct answer. So that's how we solve this question. Let us look at the next question. Which of the following structure of a molecule is expected to have 3 bond pairs and 1 lone pair of electrons? So let us draw the structures one by one and find out from those structures which of the molecules have 3 bond pairs and 1 lone pair. So let us try to write down the structures. So first will be tetrahedral. So tetrahedral, let us say you have your central molecule and you have your surrounding atoms, something like this. So this will be tetrahedral structure. And those electrons which are involved in bonding, we call them bond pairs. And those electrons which are not involved in bonding, we call them as lone pairs or non-bonding pairs. So from this structure, you can say there are 4 bond pairs. 4 bond pairs. And there are no lone pairs. So it will be 0 lone pairs. Now let us look at the second structure, trigonal planar. Here you have a central atom and you have your surrounding atoms in the form of a triangle. So it's a planar triangle. So from this you can say that the trigonal planar structure has 3 bond pairs. 3 bond pairs and once again 0 lone pairs. Now next structure is pyramidal. If you look at the structure of that pyramid, those molecules which are having that pyramidal structure, it is something like this. You have your central molecule and you have your surrounding atoms like this, and you have a lone pair of electrons here. So these are the lone pair of electrons which are not involved in bonding. So we call them as non-bonded electrons or lone pairs. So from this structure you can say that there are 3 bond pairs and 1 lone pair. So if you want me to give an example of this structure, pyramidal structure, the molecule having that pyramidal structure, you have ammonia. So you have nitrogen, hydrogen, then you have hydrogen and hydrogen. So this structure has 3 bond pairs and 1 lone pair. So the electrons which are present on top of nitrogen, though they are not involved in bonding. So we call them as lone pairs. Now let us look at the octahedral structure, how it looks. So you have your central element and you have your surrounding atoms, something like this. So this will be your octahedral structure. And if you look at this structure, there are 6 bond pairs. 1, 2, this is 1, 2, 3, 4, 5, 6. So from that you can say there are 6 bond pairs. 6 bond pairs and no lone pairs. So it will be 0 lone pairs. It will be 0 lone pairs. So that's it. So if you look at the question, they're asking you to find out a molecule which is having 3 bond pairs and 1 lone pair. So from the options given, you have this pyramidal structure with the characteristics of the question. So you can say that the option C will be the correct answer. Let us look at the next question. Which of the following is the correct electron dot structure of N2O molecule? So we have to find out the correct electron dot structure of N2O molecule. So first, whenever these kind of questions are given, first let us find out the total number of electrons that can be present in that molecule, given molecule. So only those electrons which are present in the outermost shell, we call them as valence electrons. So only those electrons can participate in bonding. So let us first find out the number of valence electrons present in N2O. So it will be N2O. So number of valence electrons on nitrogen is 5. So you have to have them, so 2 times 5, and you have oxygen 6. So it will be 10 plus 6. So total, when you draw your N2O structure, you should have 16 electrons. Now let us look at these options which are having that 16 electrons. So first one, so 2 plus 4, 6, 6 plus 4, 10, 12, 14. So this structure has 14 electrons. So this structure has 14 electrons. So definitely it will not be the electron dot structure. So when you draw your final structure, it should have that 16 electrons. Now let us look at the second option. 2 plus 6, 8, 8 plus 2, 10, 10 plus 6, 16. So this has structure. So you can say maybe B will be the answer, but we are not sure, but maybe it can be. Then let us look at the third option. So 2, 4, 8, 10, 12, 14, 16. So third option also has 16 electrons. So this also could be the answer, but we have to find out among B and C which is the answer. So, and if you look at structure D, so 2, 4, 6, 10, 12, 14. So this structure has 14 electrons. So this has 14 electrons. So obviously your final structure should have 16 electrons, but you have only 14. So definitely this will not be the structure. So it could be either B or C. So how do you find out? So to find out the actual structure, we have to know the concept called formal charges. So let us calculate the formal charges of all the atoms which are present in B and all the atoms present in C. So separately we'll calculate and then find out from that which will be the most probable structure. So how to calculate the formal charges? So there is a formula to calculate the formal charges. So formal charge is equal to number of valence electrons in the unbonded state. Number of electrons. You can say valence electrons, because only those electrons will participate in bonding. Number of valence electrons in non-bonded state minus half the number of bonded electrons. Bonded electrons plus number of electrons present in the lone pairs. Number of electrons present in lone pairs. So this is how we calculate the formal charge. So let us take structure B and calculate formal charge for each atom. First for this nitrogen, then this nitrogen, then this oxygen. So first we are looking at the structure B and calculating the formal charge for nitrogen. So number of valence electrons in non-bonded state of nitrogen will be 5 minus half the number of bonded electrons. So 3 2s are 6 plus number of electrons in lone pairs. So it will be 2. So it will be 2 3s are 6. So it will be 5 minus 5. So is equal to 0. So from that you can say that this nitrogen has the formal charge of 0. Now let us look at the second nitrogen. So that has once again 5 valence electrons in unbonded state and half the number of bonded electrons. So 3 2s are 6 plus 2 8. So it will be half times 8 plus 0, because on this nitrogen there are no lone pairs. So therefore it will be 2 4s are 8. So it will be 5 minus 4 is equal to plus 1. So this nitrogen has a formal charge of plus 1. Formal charge of plus 1. And let us look at the formal charge of this oxygen. So it will be 6 minus half the number of bonded electrons will be 2 plus number of electrons in lone pairs. So here 3 lone pairs are there. So it will be 3 2s are 6. So it will be 6. So 2 2s goes off. So it will be 6 minus 7 is equal to minus 1. So this oxygen has a formal charge of minus 1. Let us similarly calculate the formal charges in the structure C for this nitrogen, and this oxygen. So now we are calculating the formal charges in the structure C. So first nitrogen. So you have for number of valence electrons on board state is like 5 minus half the number of bonded electrons are like 4 plus number of electrons in lone pairs are once again 4. So it will be 2 2s are 4. So it will be 5 minus 6 is equal to minus 1. And if you look at the second nitrogen, it will be 5 minus half the number of bonded electrons are like, if you look at this nitrogen, you have 2 plus 2 plus 2. So it will be 8. So it will be 8 plus number of electrons in the lone pairs. So if you look at this nitrogen, there are no lone pairs. So it will be 0. So it will be 0 here. So it will be 2 4s are 8. So it will be 5 minus 4 is equal to plus 1. So let us write down the formal charges. So here it is minus 1 and here it is plus 1. And let us calculate the formal charge for this oxygen. So it will be 6 minus half the number of bonded electrons. So it will be 4 plus number of electrons in lone pairs are 4. So it will be 2 2s are 4. So it will be 6 minus 6 is equal to 0. So here the formal charge is 0. Now, how to say by looking at the formal charges which is the most stable structure? So for that there are rules to find out which one is the most stable structure. So let me write down the rules. Then from that we can find out which is the most probable structure. So what are the rules? So first rule is the structure with the least formal charges is the most stable structure. So least formal charges. So the structure with the least formal charges is the most stable structure. And the second point is when you have formal charges, negative formal charges, they should reside in the more electronegative atom. So the negative formal charge should reside on the most electronegative atom. So if you look at structure B, oxygen is having that negative formal charge, and if you know the electronegativity of nitrogen and oxygen is more electronegative compared to nitrogen. So the structure with the negative formal charge on oxygen will be the most stable structure. And if you look at C, negative formal charge is on nitrogen, which is actually less electronegative. So from that you can say that your structure B will be the most stable structure because the negative formal charge resided on the most electronegative atom. That's it. Let us look at the next question. The pressure of real gas is less than that of ideal gas because of. Now, to say something ideal gas, you have some characteristics. So if you want to say something, some gas, if you want to call some gas an ideal gas, so there shouldn't be any forces of attraction between the particles. So no forces of attraction, no intermolecular force of attraction. No intermolecular forces of attraction. So, but when you say real gas, there is intermolecular force of attraction. Intermolecular forces of attraction exist. There are intermolecular forces of attraction. So obviously, when you say intermolecular force of attraction exists, so you have the molecules closer to each other. So the situation for real gas is something like this, they're closer. But when you say ideal gas, so the particles are far apart. There are no force of attraction. So obviously, so when you say pressure, it is nothing but the force exerted by the molecules on the walls of the container. So if the molecules are far apart and keep hitting the walls very often, then you can say it's more pressure. But if the molecules are closer and they don't hit the walls very often, then you can say less pressure. So obviously, so the condition for the pressure of a real gas to be less than that of ideal gas is because of this intermolecular force of attraction. So from this, you can say that due to the intermolecular force of attraction, the pressure of a real gas is less than that of an ideal gas. So that's how we solve this question. Let us look at the next question. A reaction has both delta H and delta S negative. So what happens to the rate of reaction? So whether it increases with increase in temperature or increases with decrease in temperature, or whether if it is it going to remain unaffected by change in temperature, or cannot be predicted for change in temperature. So let us try to answer it. So whenever you say delta H is negative, so it is exothermic, we say. So in that reaction, heat is given out. So exo is nothing but given out. So therm is nothing but heat. So those reactions in which heat is given out, we call it exothermic. You also have delta H is equal to positive. So which we call it endothermic. So those reactions are favored by taking in of heat. So endo is taken in, and therm is nothing but heat. So those reactions in which heat is taken in, we call it endotherm. Now in the question, we just need to know the reaction with the characteristic delta H negative. So let us try to erase this part. Then if you look at the question, the another characteristic of this reaction is delta S is negative. So now when you say delta S, so if you say it is negative, before that, what do you mean by delta S? Delta is nothing but the entropy. So it actually indicates the disorderliness of a system. So the disorderliness. So if you say delta S is negative, obviously the disorder will be less. So you can say less disordered. The reaction is less disordered, has less disorder. And see, you can also have a situation delta S is positive. Positive. So you can say this is more disordered. More disordered. Now, when you say this reaction has delta H and delta S negative, so it is this situation. Delta H is negative and delta S is negative. So negative delta S is nothing but less disorder. So let us try to erase this part. Now, so when you say disorder, so it actually that depends on the temperature. So for example, if you have a system like this, and you have a system something like this, and you have your molecules here. Let us say this is at this system is at 100 degrees centigrade. So the molecules are comparatively closer. Let us say the same system is at 200 degrees centigrade. So if you look at the molecules, in this situation, the molecules will be much farther, because temperature we say directly proportional to kinetic energy. So more the temperature, more the energy possessing by that molecule. So they'll have a more random movement. So in this situation, you have more random movement. So from that, you can say that you want a reaction with delta S being negative. So obviously, if you want to say delta S is negative, the temperature has to be less. So it is favored by less temperature. And similarly, if you want to say that your reaction is exothermic, your reaction is actually giving out heat. So, but if you supply heat to that particular reaction, you are actually going against the reaction. So from that, you can say that if the reaction is exothermic, the reaction will be favored by less temperature. It is actually giving out heat. So obviously it should be favored by less temperature. So if you increase the temperature, the reverse reaction favors. So from that you can conclude that if you look at the option B, so it increases with the decrease in temperature. So that will be the correct answer. Increases with the decrease in temperature. So that's how we answer this kind of questions. Next question. So the equilibrium constant for a reaction given here is this much at 2000 Kelvin. In the presence of a catalyst, the equilibrium is attained 10 times faster. So equilibrium is attained definitely. If you use a catalyst, it will attain much faster. Therefore, the equilibrium constant in presence of catalyst, but they are doing the same reaction with the same temperature. So we should know that equilibrium constant changes only with temperature. Changes only with so it doesn't change with anything else. It doesn't change with pressure. It doesn't change with volume. It doesn't change with catalyst. So from this, you can say because you are doing the reaction at the same temperature, so the equilibrium constant will be same. So your answer will be D. See what happens when you use catalyst. It only fastens the rate at which it reaches the equilibrium, but it doesn't change the equilibrium constant. It only helps in reaching the equilibrium much faster. That's it. So that's the work catalyst does. So when you do the reaction at the same temperature with or without catalyst, the equilibrium constant remains the same because the temperature is same. So the point is equilibrium constant changes only with temperature. So which is why your option D will be the correct answer. Next question. So the reaction coefficient QC is useful in predicting the direction of reaction. Which of the following is incorrect? So basically when you say a reaction is at equilibrium, So to explain the situation of this reaction at equilibrium, we use Kc, which is equilibrium constant. Equilibrium constant. And now, when you say equilibrium constant, it is nothing but the ratio of your products concentration by reactants concentration. So that will be the formula for Kc, which is equilibrium constant. So this Kc we use to explain a situation of a reaction which is at equilibrium. Now let us say you have a reaction which hasn't reached equilibrium. So we call it non-equilibrium. It's not under equilibrium condition. So it didn't reach the equilibrium condition. So in that condition, we use concept called QC. So that you call it as a reaction coefficient. So every reaction tries to attain equilibrium. So obviously you have different conditions if you look at this one. So first let us say QC is less than Kc. So obviously every reaction tries to attain that Kc. If QC is less than Kc, your products has to be more to attain that QC, to make that Kc become equal to Kc. So from that you can say forward reaction favors. Forward reaction favors. And next situation is QC greater than Kc. So your Kc is actually, your QC is actually greater. So obviously to make it become equal to Kc, now your reactants has to be more. So backward reaction favors. Backward or reverse reaction, whatever. And the other situation is QC is equal to Kc. You can say that in this situation, both forward and backward reactions are happening simultaneously and at the same rate. So, which is why you don't see any change in concentration. So we can say that both forward and backward reactions are happening simultaneously and at the same rate. Simultaneously and at the same rate. So let us say if a system has reached equilibrium, you cannot say that the reaction stopped. The reaction is happening, but they are happening at the same rate. So now let us try to answer it. So first option is if QC is greater than KC, the reverse reaction is favored. Yeah, backward or reverse reaction. So this option is correct. But in the question, they're asking you to find out the option which is not correct. And next option is if QC is less than KC. So forward reaction favors. So that is also fine. And if QC is equal to KC, no reaction occurs. So this is not correct because the reaction is happening. Only thing you cannot observe the change because both forward and backward reactions are happen at the same rate. And the fourth situation is if QC is greater than KC, forward reaction is favored. If QC is greater than KC, backward reaction is favoring. So option, once again, D will be the incorrect option. So from this, you can say that option C or D will be the correct answer. Either you write C or D. Both of them will be awarded marks. So it can be either C or D. Okay, the next question is this. ClO minus gives rise to, basically 3ClO minus gives rise to ClO minus plus 2Cl minus. So we have to find out this example. So we have to find out this reaction, whether it is an oxidation reaction or reaction or disproportionation reaction or decomposition reaction. So when you say disproportionation reaction, it is basically a reaction in which the same element is undergoing both oxidation and reduction. So same element undergoes both oxidation and reduction. So in that reaction, if a same element undergoes both oxidation and reduction, you call it disproportionation reaction. So to find out what kind of reaction is this given reaction, let us find out the oxidation numbers. So we need not worry about the coefficients. So we just write ClO minus gives rise to ClO minus plus Cl minus. So here, if you look at the oxidation states, so oxygen is always -2. So whichever you don't know, consider that as x. So it will be x minus 2 is equal to -1. X is equal to 2 minus 1, which is nothing but 1. So your chlorine here will be +1. Obviously, if you look at this ClO minus, chlorine will be +1 and oxygen is always -2. And whenever you have a ion, so the charge present on that will be equivalent to the oxidation number. So here it will be -1. So now there is a change in oxidation state from +1 to -1. So basically this is decrease in oxidation state. So decrease in oxidation state, you call it reduction. So you have definitions: increase in oxidation state. Increase in oxidation state, you call it oxidation. Decrease in oxidation state, you call it reduction. So because in this given reaction, the oxidation number of chlorine is getting reduced. So from that you can say reduction is the correct answer. Another way of simply answering this question is this. So if you look at ClO minus, so in the product, one of them is just ClO minus, but the other one is Cl minus. It is actually losing oxygen. So loss of oxygen is also reduction. So that is just simple way of to answer this. So you can say that loss of oxygen will be reduction. Or if you want to say gain of oxygen will be oxidation. So because here the element is compound is losing oxygen, you can say reduction will be the correct answer. In the manufacture of hydrogen from water gas, which of the following is correct statement? So how do we manufacture hydrogen from water gas? So the reaction actually happens this: CO, water gas CO plus H2. So this water gas, we pass it over a catalyst in the presence of steam. So the reaction happening is this. So you have a catalyst, and these gases are passed over the catalyst, and the reaction happening is carbon monoxide. This gets oxidized to carbon dioxide, and you have hydrogen being formed. So you can always balance equations. So 4 hydrogens on the left, so it will be 2 here. So oxygens 2 on the left, on the right, so balanced. Now this carbon dioxide which is formed, you pass it over alkali, which is NaOH. See here, carbon dioxide is a gas and hydrogen is also gas. So obviously you should remove that carbon dioxide gas so that you can actually isolate the hydrogen. So it forms Na2CO3 plus water. So to balance this, you can put 2 here. So oxygens are 4, balanced, 2 hydrogens balanced. So this is how you actually make a hydrogen using water gas. So from this, you can say that first option will be the correct answer. So carbon monoxide is getting oxidized to carbon dioxide. You see, carbon monoxide is getting oxidized to carbon dioxide in the presence of steam, with steam in the presence of catalyst. So this is basically you have water which is in the presence of steam in the vapor state, whatever, and they're reacting on the catalyst to form carbon dioxide and hydrogen. So this carbon dioxide you pass it over alkali and you get salt and water. So this hydrogen gas you can separate it off. Okay, next question is plaster of Paris is represented as. So this is a simple question. So plaster of Paris has a general formula of calcium sulfate hemihydrate. So calcium sulfate, because it is half, you call it hemi. So it will be hemihydrate. Hemihydrate. So this you call it plaster of Paris. Or you can just simply say POP. So you have calcium sulfate dihydrate. This is actually gypsum. So from this we can say option A will be the correct answer. Addition of mineral acid to an aqueous solution of borax. The following compound is formed. So what compound is formed when you add borax to a mineral acid? So borax is a formula of Na2B4O7. So if it reacts with aqueous, like if the aqueous solution of borax reacts with mineral acid, let us say HCl, it actually forms a salt, which is NaCl and H3BO3. So this we call it orthoboric acid. Orthoboric acid. So you can always balance equation. So you have 4 borons on the left, so it will be 4 here. So 4 3 is 12 hydrogens. So so it will be, you can put 12 here. So it will be how much? So if you put, sorry, 12 hydrogens, so it will be 12 here, that's fine. Then you also have water here on the left side. So because it is, because the solution is aqueous solution of borax, you can have water on the left. So it will be, but you have 2 Na on the left. So if you put 2 Na here, it will be 2 Cl, then you have to be 2 here, then it has to be total 12 hydrogens are there. So 5 2s are 10 plus 2 12. So this is how you balance it. You can also look at this equation, so which is Na2B4O7. Let us say instead of putting in HCl, let us put now this aqueous borax in H2SO4. So you have plus H2SO4 plus H2O. So gives rise to salt, which is Na2SO4 plus H3BO3, once again, orthoboric acid. So now how to balance this? So once again 4 borons, so it will be 4 here. So 4 3 is 12 hydrogens, so 2 here and 1 sulfur, that is fine. So 12, you can put 5 here. So it will be 5 oxygens, 9 plus 7 16. So it will be 4 3 is 12 plus 4 16. So equation is balanced. So from this you can say when you add an aqueous solution of borax to mineral acid, so you get orthoboric acid, which is option B. Identify the correct statement in the following. N-butane and isobutane are functional isomers. Dimethyl ether and ethanol are chain isomers. Propane 1-ol and propane 2-ol are position isomers. Ethanoic acid and methyl methanoate are position isomers. Let us look at one by one and then answer it accordingly. So if you say N-butane, so you have 4 carbon atoms in a straight chain. So whenever I write the structure, you can always put hydrogens to satisfy the valency of carbon. So you can always put hydrogens here, hydrogens. So this will be your N-butane. So when you say N-butane, all carbon atoms are in a straight chain. And you have isobutane. Isobutane structure is basically this, with a one branch. So iso is nothing but you have a branch at the last but one carbon. So you can always put hydrogens here. So it will be CH3 and here CH and CH3. So if you look at these two structures, they are just the chain length is changing, the main chain length. So from that we can say that these two are basically chain isomers. Chain isomers. So they are not functional isomers. So option A will be wrong. Now let us look at option B. So dimethyl ether is basically this CH3 OCH3, and ethanol will be CH3 CH2 OH, and here the functional group is ether, and here the functional group is alcohol. So these we call them as functional isomers because the functional group is changing. They have the same molecular formula. Both of them have C2H6O, and this also has C2H6O is the molecular formula. Molecular formula is same, but the functional group is different. So we call them as functional isomers. So not chain isomers. So option B will be once again wrong. Let us look at option C. Propane 1-ol. So it's an alcohol, but the functional group alcohol is on the first position. So this is propane and 1-ol. And you can always balance the number of hydrogens. You can always put hydrogens to satisfy the valency of carbon. So this will be propane 1-ol. And propane 2-ol will be this. Your OH group is on the second carbon. So here, functional group is same, OH, but the position is changing. So we can call them as position isomers because the position is changing. So obviously, C could be the answer. But let us try to look at option D also and try to see if we can eliminate that also. So if you look at option D, ethanoic acid. Oic acid is a carboxylic acid functional group. Carboxylic acid. The functional group is carboxylic acid. And if you say it is O8, whenever if a name ends with O8, you call it's an ester. You can say that the functional group present in it is ester. So once again, these are different functional groups. So they are not position isomers. In fact, they are functional isomers. So obviously, D will be the wrong answer. So that's how you answer this question. In which of the following homolytic bond fission takes place? So whenever you say homolytic, the fission actually takes like this, happens like this. So you have a bonded electrons, they break easily. Fission is nothing but breaking. So you get X dot plus X dot. And whenever homolytic fission happens, you have what are called radicals being formed. These are radicals. And you also have what is this, you call it as a homolytic fission. Homolytic fission. And you also have what is heterolytic fission. So let us say both the electrons are taken by one atom. So you get X plus plus X minus. So this you call it a heterolytic fission. Heterolytic fission. So it leads to the generation of carbocations or carbanions, we call it. But here the question is homolytic bond fission. So obviously, wherever you have that free radical mechanism, that will be the answer. So you can say that option C will be the correct answer. Okay, that's it for this session. So if you have any doubts or any questions or clarifications, you can contact this email ID. you can send a mail so to this at info@ctdedu.com, or you can even WhatsApp to this number 963-207-4524. That's it for this session. Thank you very much. Bye.